These are the answers to the AP Chemistry packet that covers Topic 2.7. On this slide, you can see Unit 2 at a glance. Unit 2 is entitled Compound Structure and Properties. In this video, we will take a look at Topic 2.7, VSEPR and Hybridization. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 2.7, VSEPR and Hybridization. Here are some essential knowledge statements from the AP Chemistry course and exam description. VSEPR theory uses the Coulombic repulsion between electrons as a basis for predicting the arrangement of electron pairs around a central atom. Both Lewis diagrams and VSEPR theory must be used for predicting electronic and structural properties of many covalently bonded molecules and polyatomic ions, including the following: molecular geometry, linear, trigonal planar, tetrahedral, trigonal pyramidal, bent, trigonal bipyramidal, seesaw, T-shaped, octahedral, square pyramidal, and square planar. Bond angles, relative bond energies based on bond order, relative bond lengths, multiple bonds, effects of atomic radius, presence of a dipole moment, hybridization of valence orbitals for atoms within a molecule or polyatomic ion. The terms hybridization and hybrid atomic orbital are used to describe the arrangement of electrons around a central atom. When the central atom is sp hybridized, its ideal bond angles are 180 degrees. For sp2 hybridized atoms, the bond angles are 120 degrees, and for sp3 hybridized atoms, the bond angles are 109.5 degrees. Bond formation is associated with overlap between atomic orbitals. In multiple bonds, such overlap leads to the formation of both sigma and pi bonds. The overlap is stronger in sigma than pi bonds, which is reflected in sigma bonds having greater bond energy than pi bonds. The presence of a pi bond also prevents the rotation of the bond and leads to geometric isomers. In your packet, there is a link to visit the following website, which will take you to the PhET simulation on molecule shapes. Or you can search online for PhET, P-H-E-T, and the word shapes, and that will take you to the PhET simulation for molecule shapes. Once the website loads, you should have the following options: model and real molecules. Choose the model icon located on the left. On the bottom left side of the screen, select the box for molecule geometry. On the bottom right side of the screen, select the boxes for show lone pairs and show bond angles. So here is the PhET simulation on molecule shapes. And then we'll select model. And we'll check the box for molecule geometry and show bond angles. And then show lone pairs is also checked. Question 1. Part A. Use a separate sheet of paper to draw the correct Lewis electron dot structures for each of the following: CO2, NO2+, and HCN. And if you need more practice in drawing Lewis electron dot structures, you can watch that previous video. Topic 2.5 is on Lewis diagrams. So the first thing to do is to count the total number of valence electrons. For CO2, that's going to be 16. It's 4 for carbon, 6 for oxygen, times 2. So the Lewis electron dot structure for CO2 looks like this, with 2 double bonds. For NO2+, it's going to be 5 for nitrogen, 6 for oxygen, times 2. and that would be 17 valence electrons, but then we get to subtract 1 because it is a +1 charge, so it's going to be 16 valence electrons, and then that structure, that Lewis electron dot structure, looks very similar to the CO2 molecule. For HCN, we have only 10 electrons because it's 1 for hydrogen, 4 for carbon, 5 for nitrogen. And we draw a single bond between the carbon and the hydrogen, and a triple bond between the carbon and the nitrogen. Now on to part B. Use the PhET simulation to build each molecular ion and fill in the information below for the geometry or shape and the bond angle. So in the PhET simulation, on the right side of the screen, you can click to add or remove lone pairs of electrons, and you can click to add or remove different types of bonds. So if I'm going to make the model for carbon dioxide, that would be 2 double bonds. And in the lower left corner, we can see that the molecular geometry would be linear, and the bond angle is 180 degrees. If instead we make a single bond and a triple bond, like the HCN molecule, we can see that the shape of the molecule is still linear and the bond angle is 180 degrees. So in your packet for question 1, part B, we can say that the geometry or the shape is linear and the bond angle is 180 degrees. All right, moving on to question 2. Part A, use a separate sheet of paper to draw the correct Lewis electron dot structures for each of the following: BF3, SO3, and NO3-. So first we'll start by counting the total number of valence electrons. So for BF3, that would be 3 for boron, plus 7 for fluorine, times 3. That's a total of 24 valence electrons, and the Lewis electron dot structure would look like this, with 3 single bonds. Again, you may recall in the previous video, we talked about, because of formal charges, why boron is an exception to the octet rule, having less than an octet around the central atom. For SO3, the number of valence electrons would be 6 for sulfur and 6 for oxygen, times 3, again, a total of 24. And the SO3 Lewis diagram would look like this. And I have 2 single bonds and 1 double bond in this structure. For NO3-, it's going to be 5 for nitrogen plus 6 for oxygen times 3. That would be 23 valence electrons, but we get to add 1 more for the -1 charge, so it would be 24 valence electrons. And that Lewis diagram is very similar to the SO3 molecule. Now, in the previous video, it talked about resonance. There actually are 3 different resonance structures for SO3 and for the NO3-, the nitrate ion. I'm just showing one of those 3 possible resonance structures. Part B, use the PhET simulation to build each molecular ion and then fill in the information for the geometry or the shape and the bond angle. So the BF3 molecule with 3 single bonds has the molecule geometry of trigonal planar, and the bond angles are 120 degrees. If instead we do 2 single bonds and 1 double bond, the molecular geometry is the same. It's trigonal planar, and the bond angles are 120 degrees. So the answer to question 2, part B, is trigonal planar, and the bond angle is 120 degrees. All right, let's move on to question 3. Part A, on a separate sheet of paper, draw the correct Lewis electron dot structure for CF4, NH4+, and SO4 2-. So CF4, that would be 4 for carbon, plus 7 for fluorine, times 4, that's 32 valence electrons, and the Lewis dot structure would look like this, with 4 single bonds. With the NH4+ ion, ammonium, it's going to be 5 for nitrogen, plus 1 for hydrogen, times 4, that would be 9 valence electrons, and then we subtract 1 electron for the +1 charge, so that's going to be 8 valence electrons, 4 single bonds, like this. And then the SO42- or the sulfate ion, 6 for sulfur, plus 6 for oxygen times 4, that would be 30 valence electrons, and then we add 2 more to the total for the -2 charge. So 32 valence electrons, very similar to the CF4 molecule. This is the polyatomic ion, sulfate. Now let's take a look at the PhET simulation to see what the geometry and the bond angle would be. So when we use the PhET simulation to build a molecule or a polyatomic ion that has 4 single bonds, the molecule geometry is tetrahedral and the bond angle is 109.5 degrees. So the answer to number 3, part B, is tetrahedral for the shape and 109.5 for the bond angle. All right, moving on to question 4. Use a separate sheet of paper to draw the correct Lewis structure for PF5, phosphorus pentafluoride. You may recall from the previous video that PF5 is an example of a hypervalent molecule, which breaks the octet rule as the central atom has more than an octet. So to count the number of valence electrons, it will be 5 for phosphorus plus 7 for fluorine times 5. That's 40 valence electrons. We'll put the phosphorus atom in the center, and we have 5 single bonds to that phosphorus atom. Now let's use the PhET simulation to build this molecule. So when we use the PhET simulation to build this molecule, we need 1, 2, 3, 4, 5 single bonds. So the molecule geometry is called Trigonal bipyramidal, and as I move this molecule around, you can see that the bond angle is 90 degrees between this top atom and the 3 atoms in the middle. But if I rotate the molecule, you can see that in that center area, the bond angle is 120 degrees. So it's 120 degrees between the middle, and it's 90 degrees between the top and that center plane. And the answer to number 4, part B, is that the shape is trigonal bipyramidal, and we can see that the bond angle is either 90 degrees or 120 degrees. And now on to question 5. We're going to draw the Lewis electron dot structure for sulfur hexafluoride, SF6. So to count the total number of valence electrons, it would be 6 for sulfur plus 7 for fluorine times 6. And that's a total of 48 valence electrons. This is another example of a hypervalent molecule in which the central atom has more than an octet. So put the sulfur in the middle, and we have a total of 6 single bonds to that sulfur atom. Now let's use the PhET simulation to build this molecule. So when we use the PhET simulation to build this molecule, we need 1, 2, 3, 4, 5, 6 single bonds. And we can see that the molecule geometry is called octahedral, and no matter how I rotate this molecule, all of the bond angles are 90 degrees. So the answer to number 5, part B, is that the shape is octahedral and the bond angle is 90 degrees. Now I'd like to talk about electron domains and VSEPR. An electron domain refers to a bond, single, double, or triple, or a lone pair of electrons. A single bond or a multiple bond counts as one electron domain. A lone pair or non-bonding pair of electrons counts as one electron domain. VSEPR stands for valence shell electron pair repulsion. The electron domains that are connected to the central atom are arranged in three-dimensional space in such a way that they are located as far apart from each other as possible in order to minimize the repulsions between them. In this table, we see that 2 electron domains refers to linear with a bond angle of 180 degrees. 3 electron domains refers to trigonal planar with a bond angle of 120 degrees. 4 electron domains, tetrahedral, 109.5 degrees. 5 electron domains, trigonal bipyramidal, 90 and 120 degrees. and 6 electron domains, octahedral, 90 degrees. Up until this point in the packet, each substance that has been used, as an example, has had a central atom with no lone pairs of electrons on it. In other words, all of the electron domains connected to the central atom have been bonding domains only. Now we will consider how the shape of a molecule is affected by the presence of non-bonding electron domains on the central atom. Number 6. Each example in the table below represents a molecule with at least one lone pair of electrons on the central atom. Use the PhET simulation to build each molecule according to the information in the table. Fill in the information for molecular geometry in the table below. So our first example in this table would be 2 bonding domains and 1 non-bonding domain. So let's add 2 bonds and 1 lone pair, and we can see that the shape of this molecule would be bent. We will also get a bent shape if we use a single bond and a double bond and a lone pair. The shape of the molecule would still be bent. All right, our next example is 3 bonding domains and 1 non-bonding domain. And if we build that molecule, 1, 2, 3 bonds and 1 lone pair, we can see that the shape of this molecule is trigonal pyramidal. Okay, our next example in the table would be 2 bonding domains and 2 non-bonding domains. So let's add 2 bonds and 2 lone pairs. And we can see that the shape of this molecule is bent. The next example in the table is 4 bonding domains and 1 non-bonding domain. Okay, so here are 4 bonds and 1 lone pair. And the name of this particular shape is seesaw, and that's because it resembles the appearance of a seesaw. All right, looking at our next example in the table, we need 3 bonding domains and 2 non-bonding domains. Okay, let's add 3 bonds, 1, 2, 3, and 2 lone pairs. So the name of this particular molecule is T-shaped. Now the next example is 2 bonding domains and 3 non-bonding domains. So when we add 2 bonds and 3 lone pairs, the shape of the molecule turns out to be linear. Next example, 5 bonding domains and 1 non-bonding domain. Okay, let's add 5 bonds, 1, 2, 3, 4, 5, and 1 lone pair. And the name of this particular shape is square pyramidal. And the last example in this table is 4 bonding domains and 2 non-bonding domains. All right, let's add 4 bonds and then 2 lone pairs. And the name of this particular shape is square planar. Okay, so just to summarize, number 6, 2 bonds, 1 lone pair, that would be bent. 3 bonds, 1 lone pair, trigonal pyramidal. 2 bonds, 2 lone pairs, bent. 4 bonds, 1 lone pair, seesaw. 3 bonds, 2 lone pairs, T-shaped. 2 bonds, 3 lone pairs, linear, 5 bonds, 1 lone pair, square pyramidal, and 4 bonds, 2 lone pairs, square planar. All right, now let's take a look at number 7. It says fill in the table below with one of the following example molecules. So there are a total of 13 example molecules to be placed in this table. And on this slide, you're not looking at the entire table, but just a portion of it. I'm assuming that you have already had the chance to draw the Lewis electron dot diagram for each one of these 13 molecules. If that's not the case, then go ahead and pause this video and then take some time on a separate sheet of paper to draw the Lewis diagram for each one of these molecules. That way, when I discuss the number of bonding domains and non-bonding domains, you can verify that you've already had a chance to create these Lewis diagrams. The first Lewis diagram that I'm going to show you is for carbon dioxide. We've already talked about this molecule earlier, and you can see with carbon dioxide there is a total of 16 valence electrons that were used to create this Lewis diagram. And if I count up the fact that 16 is a multiple of 8, I have 2 groups of 8. And you'll notice that there are no extra electrons, there's no lone pairs, no non-bonding domains on the central atom. So where this fits in the table is in that first row where it says 2 bonding domains and 0 non-bonding domains. Now, if I go from 16 valence electrons to 18 valence electrons, assuming that the terminal atoms have a complete octet, which is a group of 8, I'm going to have 2 bonding domains, but I will also have 2 electrons left over as a lone pair on the central atom. So this would correspond to the molecule sulfur dioxide, or SO2. Again, here is a group of 8. Here is another group of 8. So 8 plus 8 is 16. And then that last pair of electrons is a lone pair on the central atom. So where this fits in the table would be 2 bonding domains and 1 non-bonding domain. If we go from 18 valence electrons to 20 valence electrons, now that molecule will still have 2 groups of 8, as in 2 bonding domains attached to the central atom, but then there'll be 4 electrons, and you'll place them in the form of 2 lone pairs on the central atom. Again, the molecule that corresponds to this would be sulfur difluoride, or SF2. So there's a group of 8, there's a bonding domain. There's another group of 8, another bonding domain, but then there are 4 more electrons that are located on the central atom, so that's 2 non-bonding domains. Again, that would correspond to that particular row of the table. 2 bonding domains, 2 non-bonding domains. So what I'm trying to do is, because each of these examples have terminal atoms that have a complete octet, so in other words, there's no hydrogen atom where you wouldn't have that complete octet, I can think in terms of multiples of 8. So when I have a multiple of 8, like 16, for example, then there will be no electrons left over on the central atom. But if I have a total number of valence electrons that is not a multiple of 8, I can think in terms of the leftover electrons being placed on the central atom. So far, I've shown you 3 example molecules in which the total number of valence electrons was 16, 18, and 20. The next number I'm going to take a look at is 24 valence electrons. Again, because 24 is a multiple of 8, then I'm thinking there's going to be 3 bonding domains. So the example molecule that would correspond to 24 valence electrons is sulfur trioxide, SO3. And by the way, I'm not showing all of the resonance structures for things like SO2 and SO3, just one valid Lewis diagram to determine where that would fit in the table. But as you can see, there are 3 bonding domains, and there are no extra electrons, no non-bonding domains on the central atom. So this would correspond to 3 bonding domains, 0 non-bonding domains, and we've already seen that SO3 is trigonal planar. My next total is 26 valence electrons. So now, because I have 2 extra electrons, then there will be 1 non-bonding domain on the central atom. So 26 valence electrons, that corresponds to phosphorus trifluoride, or PF3. So there's a group of 8, that's a bonding domain, another group of 8, another bonding domain, another group of 8, so 3 bonding domains, but then this last pair of electrons in the form of a lone pair on the central atom, that is 1 non-bonding domain. So there's PF3 in the table. And then the last molecule for this particular set of the table that I want to talk about, the last number of valence electrons to consider, is 32. So you can imagine that since 32 is a multiple of 8, we're going to have 4 bonding domains. So the molecule that would have 32 valence electrons is carbon tetrafluoride, CF4. Again, here are 4 groups of 8, and there are no extra non-bonding electrons or lone pair of electrons on the central atom. So 4 bonding domains and 0 non-bonding domains. Now, as we explore the next part of the table, all of these will be the so-called hypervalent molecules in which there is more than an octet on the central atom. But that same system applies. If you have the total number of valence electrons and it's not a multiple of 8, then most likely the extra electrons will be located on the central atom. So again, just to remind you that this pattern that I'm talking about, where we're considering multiples of 8, that only works if each of the terminal atoms in the Lewis diagram has access to a complete octet. So for example, the top structure is CF4, which has 32 valence electrons. The bottom structure is CH2F2, which has a total of 20 valence electrons. They both contain 4 bonding domains and 0 non-bonding domains, but the reason why 20 is not a multiple of 8 is because the hydrogen atoms in that structure, in that Lewis diagram, they do not have a complete octet. So as you know, hydrogen only needs access to 2 valence electrons to complete its valence shell. So all of the examples that I've chosen in question 7 of this packet have terminal atoms like oxygen and fluorine, which do have a complete octet. All right, so the next part of the table we're going to take a look at are all those hypervalent molecules. And the first number of valence electrons that I'm going to consider is the number 40. And since 40 is a multiple of 8, I'm expecting 5 bonding domains and 0 non-bonding domains, which is what we see for the molecule phosphorus pentafluoride, or PF5. So 1, 2, 3, 4, 5. Again, 5 times 8 is 40. So PF5 belongs in that particular section of the table. And then the next example for the total number of valence electrons that I'd like to consider is 48. So 48 is also a multiple of 8, and I would expect 6 bonding domains and 0 non-bonding domains. And that's what we see with the molecule sulfur hexafluoride, or SF6. So 1, 2, 3, 4, 5, 6. 6 times 8 is 48. So SF6 is 6 bonding domains and 0 non-bonding domains. Now, the other examples that we have not talked about yet that belong in the table, all of them will feature a total number of valence electrons that is not a multiple of 8. So if you take the total number of valence electrons and divide by 8, then whatever is left over or remainder in that calculation, those electrons are going to be placed in the form of lone pairs on the central atom. So the next number of valence electrons that I'd like to consider is the number 34. So to process the number 34, 8 times 4 is 32. And then I would need 2 electrons to be located on the central atom. So 34 valence electrons corresponds to the molecule sulfur tetrafluoride, or SF4. So here are 4 bonding domains. Again, 4 times 8 is 32. And there's 1 lone pair on the central atom. So SF4, which has seesaw geometry, 4 bonding domains, 1 non-bonding domain. The next number of valence electrons I'd like to consider is the number 28. Again, how many times can 8 go into 28? Well, 8 times 3 is 24, but there's going to be 4 extra electrons left over, which we will place in the form of lone pairs on the central atom. So the molecule that has 28 valence electrons is chlorine trifluoride, or ClF3. So there are my 3 bonding domains. 3 times 8 is 24, and there are 2 lone pairs on the central atom. So 3 bonding domains, 2 non-bonding domains, and the molecular geometry of ClF3 is T-shaped. The next number of valence electrons to consider is the number 22. 22 is not a multiple of 8. 8 times 2 is 16, but there's going to be 6 extra electrons left over, which we will place in the form of 3 lone pairs on the central atom. So the molecule that has 22 valence electrons is xenon difluoride. So here are the 2 bonds that are coming off the central atom to the fluorine atoms. That would be 8 plus 8 is 16. And then here are 6 valence electrons on the central atom in the form of 3 lone pairs. So xenon difluoride, XeF2, has 2 bonding domains and 3 non-bonding domains, and that is actually a linear molecule. Our next number of valence electrons, as we narrow down to the final 2 choices that we have it used in this table, 42 valence electrons. So 8 times 5 is 40. So we're going to have 5 bonding domains, and then we have these 2 electrons left over on the central atom. So 42 valence electrons would correspond to the molecule bromine pentafluoride, or BRF5. So 1, 2, 3, 4, 5 bonding domains. 5 times 8 is 40. And then 1 non-bonding domain, 1 lone pair on the central atom. So BRF5, 5 bonding, 1 non-bonding, and the molecular geometry is square pyramidal. And then finally, the xenon tetrafluoride has 36 valence electrons. 4 times 8 is 32. So there are the 4 bonding domains. But now we have 4 electrons left over. So they're placed on the central atom in the form of 2 lone pairs. So the molecular geometry of xenon tetrafluoride is square planar. Okay, before I show you question 8 of the packet, I just want to give you an example of what can happen when a lone pair or a non-bonding pair of electrons is present on the central atom and how that can affect the bond angle. So we see 2 molecules here. On the left, we see boron trifluoride, or BF3, and on the right, we see ozone, or O3. The bond angle in BF3 is 120 degrees. That's based on the trigonal planar geometry. And the bond angle for ozone is not 120, but slightly less than 120. So this difference in the bond angle can be explained as follows. Let's compare the amount of space occupied by a bonding pair of electrons with the amount of space occupied by a non-bonding pair or lone pair of electrons. A bonding pair of electrons is attracted by the nuclei of 2 atoms. Therefore, the bonding electrons are likely to be located in the space between the 2 atoms that share them. However, a non-bonding pair or lone pair of electrons can spread out more, occupying more space than a bonding pair. As a result, it tends to exert greater repulsive forces on the nearby bonding pairs, reducing the bond angle slightly. So that's why the bond angle in ozone, O3, is a little bit less than 120 degrees because the non-bonding pair exerts greater repulsion on the nearby bonding pairs. So now we come to question 8 of the packet. The Lewis structures for CH4, NH3, and H2O are shown above. arrange these three molecules in order from the smallest bond angle to the largest bond angle. So I'm going to start with CH4 because we already know from VSEPR theory that that has tetrahedral geometry and that the bond angle is 109.5 degrees. But NH3 has one lone pair of electrons on the central atom, and H2O has two lone pairs of electrons on the central atom. So a lone pair of electrons can spread out more, occupying more space than a bonding pair. As a result, it tends to exert greater repulsive forces on the nearby bonding pairs, reducing the bond angle slightly. So our prediction is that both NH3 and H2O should have bond angles that are slightly less than 109.5 degrees. And hopefully it makes sense that if you have two lone pairs on the central atom as opposed to only one lone pair on the central atom, that there should be a different level of repulsion. So two lone pairs on the central atom in the H2O molecule should exert more repulsions on the nearby bonding pairs than only one lone pair, as we see in the NH3 molecule. So our prediction is that the bond angle in H2O should be even smaller than the bond angle in NH3. That means that if we rank these molecules from smallest bond angle to largest bond angle, H2O would be the smallest bond angle, and CH4 should be the largest bond angle with NH3 in between. So now let's return to that PhET simulation, but this time, instead of clicking on model, let's click on real molecules. So I'm going to go ahead and select CH4 from the pull-down menu, and I'm going to click on the option to show bond angles. So here we can see what we would predict, which is this is tetrahedral geometry for CH4, and the bond angle is 109.5 degrees. Now when I switch to NH3 from the options, this bond angle in NH3 is not 109.5, but slightly less than that value. So it's about 107, 108. And when I switch from NH3 to H2O, I can see that the bond angle in H2O is even smaller than the bond angle in NH3. It's approximately 105 degrees. So here are the bond angles for these three molecules: 109.5 for CH4, approximately 107, 108 for NH3, and approximately 105 for H2O. All right, in order to prepare for question 9 of the packet, which has to do with the polarity of molecules, we're going to take a look at a PhET simulation that's on molecule polarity. So the link to this particular website will be located in the video description area. And once the website loads, you're going to click on the 3 atoms icon, which should be located in the middle of the screen. And you want to select the following settings, which is bond dipoles, molecular dipole, and then turn the electric field on. All right, so here we are at the website. Again, I'm going to click on the 3 atoms option. I'm going to make sure that bond dipoles and molecular dipole are checked, as well as turning the electric field on. So here are the instructions. Arrange the atoms A, B, and C so that a linear molecule is formed. The 2 black arrows represent the dipoles for each polar bond. These 2 arrows are equal in magnitude, but they point in opposite directions. These 2 dipoles cancel each other out. The yellow arrow representing the molecular dipole has disappeared. The molecule rotates randomly within the electric field because it is not attracted to either the positive plate or the negative plate. The molecule is nonpolar. Its dipole moment is equal to 0. All right, so this is the default view of the molecule as I set things up initially. So now I'm going to rotate the bonds so that the molecule is linear. And again, you can see how this is a nonpolar molecule that just rotates randomly within this electric field. Now, arrange the atoms A, B, and C so that a bent molecule is formed. The two black arrows represent the dipoles for each polar bond. These two arrows are equal in magnitude, but now they do not point in opposite directions. The two dipoles do not cancel each other out. The yellow arrow, representing the molecular dipole, is visible. The molecule does not rotate around randomly within the electric field. It is locked in place because the negative end of the molecular dipole points toward the positive plate. This molecule is polar and has a non-zero value for its dipole moment. So as I change this molecule from linear to bent, again, we can see the appearance of the molecular dipole, which is indicated by that yellow arrow. And now the molecule does not rotate randomly, but is locked in that position where the negative end of the dipole is attracted toward the positive plate. So based on the two examples that I have shown you so far with this PhET simulation, you might be thinking that if a molecule has bent molecular geometry, that it's going to be classified as polar. And that is a reasonable conclusion. That's fine. But you might think that if a molecule has linear geometry, that it will always be nonpolar. And that's not necessarily true. So take a look at this particular slide. On the left, we see a linear molecule. The bond dipoles are pointing in opposite directions, but they do not have the same magnitude. So those two dipoles are pointing in opposite direction, but the magnitude of the dipole for bond AB is greater than the magnitude of the dipole for bond BC. So they would not cancel each other out, and that would be a polar molecule. In the picture on the right, you can see that we have two bond dipoles that are pointing in the same direction. They would not cancel out. So these are two examples of linear molecules that would be considered polar. So again, it is possible to create a linear molecule that is polar. Use the sliders in the PhET simulation to adjust the electronegativity of the atoms. And if the two bond dipoles, which are represented by the black arrows, do not cancel each other out, then the molecule is classified as polar. If we can see a yellow arrow, which represents the molecular dipole, then the molecule is polar. So now here I am back at the PhET simulation. The first thing I'm going to do is turn this from a bent molecule into a linear molecule. You can see that the molecular dipole disappears, and this molecule just rotates randomly. So I'm now going to adjust the electronegativity of the atoms. So now the magnitude of the dipole for bond BC is different than the magnitude of the bond dipole for AB, and this is now a polar molecule. I'm now going to adjust the electronegativity so that these two dipoles are now pointing in the same direction. Again, this is still considered to be a polar molecule because the dipoles for the bonds do not cancel each other out. This is number 9 from the packet. Use a separate sheet of paper to draw the correct Lewis electron dot structures for each of the following molecules in the table below. Now, on this particular slide, you're not seeing the entire table, but just a portion of the table. There's a total of 17 molecules for you to draw and analyze in this question. After you draw the correct Lewis diagram, then you have to identify the molecular shape and classify each molecule as polar or nonpolar. In the PhET simulation, we were only looking at a molecule that contains 3 atoms, so some of these molecules are more complicated than that, but what I will try to do is use the following criteria, which is if all of the bond dipoles cancel each other out, then the molecule is classified as nonpolar. If the bond dipoles do not cancel each other out, the molecule is classified as polar. So our first example is CO2, carbon dioxide. It contains a total of 16 valence electrons. We have seen already in this video that it's a linear molecule. And when I draw the bond dipole, oxygen is more electronegative than carbon. So the arrow will point from the carbon to the oxygen. And based on what I have already shown you with that PhET simulation, when we have two bond dipoles that have the same magnitude but are pointing in opposite directions, then those bond dipoles will cancel each other out. That makes CO2 an example of a nonpolar molecule. So nonpolar molecules tend to be symmetrical and all of the bond dipoles cancel each other out, whereas a polar molecule tends to be asymmetrical and the bond dipoles do not cancel each other out. So our next example is the molecule HCN. It has a total of 10 valence electrons, and when you draw the Lewis diagram, this is what you get: a single bond between the hydrogen and the carbon, and a triple bond between the carbon and the nitrogen. This is classified as a linear molecule for the same reason that carbon dioxide is linear. There are two bonding domains, and there are no lone pairs of electrons on the central atom. Now, do these dipoles cancel each other out? Let's take a look. Carbon is more electronegative than hydrogen, so there is a slight dipole between the hydrogen and the carbon. And then nitrogen is more electronegative than carbon, so there is a dipole between the carbon and the nitrogen. Notice that these bond dipoles are pointing in the same direction. Even if they were pointing in opposite directions, they would not have the same magnitude and they would not cancel each other out. So the point here is that these dipoles do not cancel each other out. Therefore, HCN is classified as a polar molecule. All right, the next molecule to consider is BF3, boron trifluoride, and the total number of valence electrons for BF3 is 24. In an earlier video, I talked about how we can use formal charges to explain why the Lewis diagram of BF3 is an exception to the octet rule, where the central atom has less than an octet. Now, considering the number of bonding domains, we have 3 bonding domains, and there are no lone pairs of electrons on the central atom. Therefore, the molecular shape is trigonal planar. Now let's consider if these bond dipoles cancel each other out or not. So the bond dipole is between boron and fluorine, fluorine being more electronegative than boron. And hopefully you can see from the way that these 3 bond dipoles are arranged that they are in a symmetrical fashion in this trigonal planar molecule. So these 3 bond dipoles cancel each other out. BF3 is classified as a nonpolar molecule because of the symmetry. All of the bond dipoles in the BF3 molecule cancel each other out. The next molecule to consider is CCl2O. That's 1 carbon, 2 chlorines, and 1 oxygen. Carbon will be the central atom. If we add up the number of valence electrons for this molecule, we get 24 again. This time we have 2 single bonds between the carbon and the chlorine, and then a double bond between the carbon and the oxygen. The molecular shape is still the same as it was for BF3 because we have 3 bonding domains and there are no lone pairs of electrons on the central atom. This is a trigonal planar molecule, but let's take a look and see if these bond dipoles will cancel each other out. We have 1 oxygen and 2 chlorines. So the atoms are not the same. There is a bond dipole between the carbon and the oxygen, and there are bond dipoles between the carbon and the chlorine atoms, but they're not the same magnitude all the way around. So these bond dipoles do not cancel each other out because they have different magnitudes. The carbon-chlorine bond has a different bond dipole than the carbon-oxygen bond. So because of asymmetry, this is classified as a polar molecule because the bond dipoles do not cancel each other out. All right, the next molecule to consider is SO2. We have seen this earlier in the video. SO2 has a total of 18 valence electrons, and when you draw the Lewis diagram, you should realize that because there is one lone pair of electrons on the central atom, this molecule is not linear like CO2. This is a bent molecule. And because it is bent, the two bond dipoles are not exactly opposite. So while they do have the same magnitude, they're not pointing in opposite directions. So these bond dipoles between the S and the O are not symmetrically arranged in such a way that they cancel each other out. This is a polar molecule. So what makes it polar is the bent shape and the fact that those two bond dipoles in the SO2 molecule do not cancel each other out. The next molecule to consider is CF4, carbon tetrafluoride. The shape of this molecule is tetrahedral. We have 4 bonding domains, and the 4 dipoles, that is the bond dipole between carbon and fluorine, the 4 dipoles are arranged in 3-dimensional space to be very symmetrical. The 4 dipoles are pointing toward the corners of that tetrahedral geometry. So because of the symmetry, this is a non-polar molecule in which all 4 of the dipoles are arranged in such a way to cancel each other out. Now let's take a look at our next molecule. This is CH2F2. So when you draw the Lewis diagram for CH2F2, it's going to be similar to CF4 in that it's tetrahedral molecular shape. The difference is that all 4 of those atoms are not the same. So we have a slight dipole between the hydrogen and the carbon, and then we have a dipole between the carbon and the fluorine, but the magnitude of these 4 dipoles is not the same, and they do not cancel each other out. So because of the asymmetry, this molecule is classified as polar. So the bond dipoles in CH2F2 are not going to cancel each other out. That molecule is polar. The next molecule to consider is the molecule NH3. It has a total of 8 valence electrons, and when you draw the Lewis diagram, you're going to have 3 single bonds, and there will be 1 lone pair on the central nitrogen atom. This molecule is not trigonal planar. When you have 3 bonding domains and 1 non-bonding domain, the shape of the molecule is trigonal pyramidal. So earlier, when I was talking about SO2 and I said the fact that it was bent makes it polar, this is a similar situation. The fact that this is a trigonal pyramidal molecule, that means that the dipoles will not cancel each other out. So the 3 bond dipoles are not going to cancel each other out. NH3 is classified as a polar molecule because of that trigonal pyramidal geometry. These bond dipoles do not cancel each other out. The last molecule in this section of the table on this slide is H2O. You already know that H2O has 2 single bonds and 2 lone pairs of electrons. It is a bent molecule. And again, just like SO2, the fact that the molecule is bent means that the 2 bond dipoles are arranged in such a way that they are not exactly opposite. So they will not cancel each other out. So H2O is classified as a polar molecule because the bond dipoles do not cancel each other out. So number 9 from this packet is a rather long question because there's a total of 17 different molecules to analyze and classify into the category of nonpolar versus polar. At this point, I have discussed 9 different molecules, and I have classified them as either nonpolar or polar. So we're at roughly the halfway point in question 9. So on this slide, you can see that there are still 8 additional molecules to analyze and classify. All 8 of these molecules have something in common. They're all examples of that hypervalent situation in which in the Lewis diagram there is more than an octet of electrons around the central atom. The first molecule I'd like to consider is PF5, phosphorus pentafluoride. And you've seen this molecule before. If you remember the geometry, the molecular shape, it is classified as trigonal bipyramidal, and the bond angles are either 120 degrees or 90 degrees. So now the question is, do these 5 bond dipoles in this molecule cancel each other out or not? If you look at the 3 bond dipoles in the middle section of this molecule, they are all arranged in a trigonal planar fashion with bond angles of 120 degrees. So that symmetry would cause those 3 bond dipoles to cancel each other out, like we saw earlier with the BF3, the boron trifluoride molecule. Now, there are 2 more additional atoms of fluorine, but one is above the plane and the other is below the plane, and they're pointing in opposite directions for the bond dipoles. So based on the symmetry of this molecule, all 5 of these phosphorus fluorine bond dipoles will cancel each other out. So the PF5 molecule is classified as nonpolar. Now watch what happens when we have the exact same molecular shape, but we lose the symmetry. So what I did in the next example is I just replaced one of the fluorine atoms in this molecule with a chlorine atom. So the molecular shape is still trigonal bipyramidal. We still have 5 bonding domains, but that one chlorine being different than the other 4 fluorine atoms, that changes the symmetry of this molecule. So no longer do we have 5 equal bond dipoles. So because of asymmetry, we now have a polar molecule in which the bond dipoles do not cancel each other out. So these 2 molecules are a good example of compare and contrast. PF5 and PF4Cl. Same molecular shape, trigonal bipyramidal, but the PF5, because of symmetry, is a nonpolar molecule in which all the bond dipoles cancel each other out. PF4Cl, because of asymmetry, the bond dipoles do not cancel each other out, so it's polar. Our next example in the list is SF4, sulfur tetrafluoride. You have seen this molecule before. There's going to be 4 bonding domains and 1 non-bonding domain. There's a lone pair of electrons on the central atom. So what that does is it creates a molecular shape that is known as seesaw. These 4 sulfur fluorine bond dipoles are not arranged symmetrically in 3-dimensional space around the central atom so that they don't cancel each other out. So because of the asymmetry of this particular shape, this molecule is classified as polar. So SF4, with its seesaw geometry, is polar because the bond dipoles do not cancel each other out. The next molecule to consider is chlorine trifluoride. It's going to have 3 bonding domains and then 2 lone pairs on the central atom. So ClF3 has a molecular shape that is known as T-shaped. So it's not trigonal planar. Because of the arrangement of these bond dipoles in this T-shaped molecule, they're not going to cancel each other out. So because of the asymmetry, because of the fact that the bond dipoles in the T-shaped molecule of ClF3 do not cancel each other out, ClF3 is classified as polar. Our next example is xenon difluoride, XeF2. It's going to have 2 bonding domains and 3 lone pairs of electrons on the central atom. So for that particular molecule, the molecular shape is linear. The 2 bond dipoles are the same magnitude and pointing in opposite directions. So like we saw earlier with carbon dioxide, these 2 bond dipoles in this linear molecule are going to cancel each other out. So XeF2, xenon difluoride, is classified as a nonpolar molecule because of symmetry. The 2 bond dipoles in that molecule will cancel each other out. All right, the next molecule in the list is sulfur hexafluoride, SF6. There are 6 bonding domains. The shape of the molecule is classified as octahedral. And because all 6 of these bond dipoles are arranged in 3-dimensional space in a very symmetrical fashion, then all 6 of these bond dipoles will cancel each other out. SF6 is classified as nonpolar because all of the bond dipoles cancel each other out. Next example, BRF5, so bromine pentafluoride. We have 5 bonding domains, but then there is also a lone pair of electrons on the central atom. The molecular shape is square pyramidal, and in these 5 dipoles, 4 of them might cancel each other out in that square planar arrangement, but there's a 5th atom of fluorine above the plane, and there's nothing below the plane to cancel out that dipole. So because of asymmetry, BRF5 is classified as polar because these 5 bond dipoles do not cancel each other out. Now, speaking of square planar, XeF4, xenon tetrafluoride, it has 4 bonding domains, 2 non-bonding domains. The geometry, the molecular shape is square planar, and as you can see, all 4 of these, because they lie in the same plane and they have the same magnitude, these 4 bond dipoles are arranged symmetrically, and they would cancel each other out. So we classify XeF4 as nonpolar because of symmetry. All the bond dipoles in that molecule cancel each other out. Now, before we take a look at question 10 in this packet, I'd like to give you some background information about the topic of hybridization. Remember that topic 2.7 is entitled VSEPR and hybridization. On this slide, you can see the essential knowledge statements from the AP Chemistry course and exam description for topic 2.7. And so far in this video, I've talked about concepts related to VSEPR theory, which is valence shell electron pair repulsion theory, and that includes such things as molecular geometry, the shapes of molecules and polyatomic ions, bond angles, the presence of a dipole moment, in other words, whether a molecule is classified as polar or nonpolar. But so far in this video, we haven't yet seen examples involving the hybridization of valence orbitals for atoms within a molecule or polyatomic ion. The terms hybridization and hybrid atomic orbital are used to describe the arrangement of electrons around a central atom. When the central atom is sp hybridized, its ideal bond angles are 180 degrees. For sp2 hybridized atoms, the bond angles are 120 degrees. And for sp3 hybridized atoms, the bond angles are 109.5 degrees. So here in this table, you can see that there's sp, sp2, and sp3 in that first column on the far left-hand side. In order to explain how the atomic orbital for an atom forms chemical bonds to create molecules with certain molecular shapes, we assume that the atomic orbitals on an atom undergo a mixing process that is known as hybridization. And the 3 types of hybrid orbitals are summarized in the table below. So sp involves the mixing of one s orbital and one p orbital for a total of 2 electron domains around the central atom with an arrangement that is 180 degrees. sp2 hybridization involves a mixing process where one s orbital and 2 p orbitals are combined together. That's a total of 3 electron domains that are arranged in a 120 degree arrangement, trigonal planar. And if the hybridization is known as sp3, one s orbital and 3 p orbitals are mixed together for 4 electron domains around the central atom with an arrangement of 109.5 degrees in a tetrahedral geometry. So focusing on carbon for just a moment, carbon has 4 valence electrons. So this particular picture of the 4 orbitals with 2 electrons in the 2s orbital and 2 electrons in the 2p subshell, this picture for the valence electrons of carbon doesn't fully explain why a carbon atom forms 4 equivalent bonds with 4 hydrogen atoms in a molecule such as CH4. In order to explain the bonding and the geometry of the CH4 molecule, the atomic orbitals of carbon are mixed in a process known as hybridization. So now 1 s orbital and 3 p orbitals are combined to produce 4 equivalent sp3 orbitals. Now, I do understand that the concept of hybridization of atomic orbitals can be confusing for chemistry students to understand. What I'm doing in this video is giving you a brief overview of how it works, as well as specific guidelines for what to look for in a Lewis diagram to determine the hybridization of the central atom in a molecule or polyatomic ion. So, in sp3 hybridization, this is how it works. 1 s orbital and 3 p orbitals are hybridized to produce 4 orbitals with the same energy. These 4 orbitals are called sp3 orbitals, and they are oriented in 3-dimensional space with a tetrahedral arrangement with angles of 109.5 degrees. The next type of hybridization is called sp2. So when 1 s orbital and 2 p orbitals are hybridized, it produces 3 orbitals with the same energy, and they're called sp2 orbitals. And they're oriented in 3-dimensional space with a trigonal planar arrangement with angles of 120 degrees. And the last type of hybridization is called sp. So when 1 s orbital and 1 p orbital are hybridized, it produces 2 orbitals with the same energy. They're called sp orbitals, and they are oriented in a linear arrangement with an angle of 180 degrees. So again, looking back at this summary, the hybridization is either sp, sp2, or sp3. The total number of electron domains around the central atom is either 2, 3, or 4. So you can focus on the total number of electron domains around a particular atom in a Lewis diagram, and that will help you get the correct hybridization. So here are the instructions in question 10. Identify the hybridization of the valence orbitals, sp, sp2, or sp3, around the central atom in each of the following substances. Draw the Lewis diagram in order to determine the total number of electron domains around the central atom. So the first Lewis diagram that we have to draw is for a molecule BeF2. And this is a rather unusual molecule because it is similar to BF3, where the central atom has less than an octet. So beryllium has 2 valence electrons, and fluorine has 7 valence electrons, and there are 2 of them in the molecule. So that would be 16 valence electrons. It's going to have 2 single bonds, an exception to the octet rule, and we can use formal charges to explain why beryllium will have less than an octet, very similar to the pattern with boron trifluoride. And so now that we know that there are 2 electron domains, that would correspond to sp hybridization. So that's how it works for all of these examples. Count the number of electron domains around the central atom, and then that will give you the answer for the hybridization. So BF3, another exception to the octet rule because it does not have a complete octet, 3 for boron, plus 7 for fluorine, times 3, that would be 24 valence electrons, 3 electron domains. Therefore, the hybridization of the central atom is sp2. Our next example is carbon tetrafluoride, CF4, 4 for carbon, 7 for fluorine, times 4, that's a total of 32 valence electrons. Here's the Lewis diagram, 4 electron domains, and that would correspond to a hybridization of sp3. All right, our next example is carbon dioxide, CO2. 4 valence electrons for carbon, 6 for oxygen, times 2, that's 16 valence electrons. And when you draw the Lewis diagram for CO2, this is what it looks like with 2 double bonds, and there are no lone pairs of electrons on the central atom. What can be confusing for chemistry students is whether or not that double bond counts as 1 or 2 electron domains. And here's the answer. An electron domain refers to a bond, whether it's single, double, or triple, doesn't matter. A single bond or a multiple bond counts as 1 electron domain. And although there are no lone pairs of electrons on the central atom, a lone pair of electrons does count as an electron domain. So we'll see that in future examples. But for this molecule, CO2, 2 electron domains, sp, hybridization. All right, moving on to sulfur dioxide, or SO2. 6 for sulfur, 6 for oxygen, times 2, that's 18 valence electrons. So our Lewis diagram looks like this, with 2 bonding domains and 1 non-bonding domain on the central atom. That's a total of 3 electron domains. Therefore, the hybridization of the central atom is sp2. All right, next example, sulfur difluoride, SF2. 6 for sulfur, 7 for fluorine, times 2. So we have 20 valence electrons, and our Lewis diagram looks like this. 2 bonding domains, 2 non-bonding domains, that is a total of 4 electron domains around the central atom. Therefore, the hybridization is sp3. All right, our next example is a molecule known as ammonia, NH3. 5 valence electrons for nitrogen, plus 1 for hydrogen, times 3. That's 8 valence electrons total. Nitrogen is going to form 3 single bonds, and there's going to be a lone pair of electrons on the central atom. So therefore, that's 3 bonding and 1 non-bonding domain. 4 electron domains around the central atom, sp3 hybridization. Now we go from ammonia, the molecule, to ammonium, the polyatomic ion. There's going to be a total of 5 valence electrons, plus 4 for the 4 hydrogens, but then you subtract 1 for the positive charge. So that's going to be a total of 8 valence electrons. Clearly, we have 4 electron domains around the central atom. So this is also sp3 hybridization. Next example is water. Water has 8 valence electrons total, 2 bonding domains and 2 non-bonding domains, 4 total electron domains around the central atom. This is also sp3 hybridization around that central oxygen atom. Our next example is NO2+, the polyatomic ion. So that's 5 for nitrogen plus 6 for oxygen times 2. That would be 17 electrons, but then we subtract 1 from the total for the positive 1 charge. So it's 16 valence electrons. We have already seen what carbon dioxide looks like with a total of 16 valence electrons. Therefore, this Lewis diagram looks very similar to the Lewis diagram for carbon dioxide. Remember that a double bond still counts as 1 electron domain. So we have no lone pairs on the central atom. 2 electron domains would correspond to a hybridization of sp for the central nitrogen atom. Now we have NO2-, so a different polyatomic ion. 5 for nitrogen plus 6 for oxygen times 2. That would be 17 electrons, but now we get to add 1 more to the total for the negative charge. So now it's 18 valence electrons. Very similar to the Lewis diagram for SO2. So we have 2 electron domains that are bonding, and then 1 electron domain that is non-bonding. A total of 3 electron domains around the central atom. So the hybridization of the central atom is sp2. Now we have the last example here. This is NO3- or nitrate. 5 for nitrogen plus 6 for oxygen times 3. That would be 23 electrons. We add 1 more for the negative charge. 24 valence electrons. There are 3 resonance structures for this, but that's not important for us to determine that there are still going to be 3 electron domains, and the hybridization of the central atom is sp2. All right, let's take a look at question 11 from your packet. In the reaction above, how does the hybridization of the carbon atoms change? So remember that we're looking for the total number of electron domains around the central atom to determine the hybridization. So the first molecule I'm going to analyze is the one that's on the far left side of the screen. And I see a carbon atom on the left, which contains 3 electron domains around it. There's no lone pairs on that carbon, but I see 3 bonding domains. Therefore, that would be sp2 hybridized. Now, the next carbon in that same molecule also has 3 electron domains, 3 bonding domains. So that is also sp2 hybridized. So as far as the correct answer to this question, we know it's changing from sp2 to something else. So the correct answer is either C or D. On the right side of the equation, I see a carbon with 2 electron domains and no lone pairs on the central atom. So 2 bonding domains, that would be sp, and the other carbon in that same molecule also has 2 bonding domains, sp. So the answer to this question is that the hybridization is changing from sp2 to sp for those carbon atoms. So the correct answer is D. Now, before we take a look at question 12 in this packet, I'd like to highlight on this slide the final essential knowledge statement from the AP Chemistry course and exam description for topic 2.7. And this essential knowledge statement has to do with the concept of sigma and pi bonds. It says, bond formation is associated with overlap between atomic orbitals. In multiple bonds, such overlap leads to the formation of both sigma and pi bonds. The overlap is stronger in sigma than pi bonds, which is reflected in sigma bonds having greater bond energy than pi bonds. The presence of a pi bond also prevents the rotation of the bond and leads to geometric isomers. So for the remainder of this video, I'm going to explain information about sigma and pi bonds as it relates to question 12 in this packet. So if you're confused about what exactly is the difference between a sigma bond and a pi bond, I'm going to explain it in a very general way, and then I will tell you exactly what you need to know and look for in a Lewis diagram or a structural formula of a molecule to count the number of sigma and pi bonds in a molecule. So a sigma bond is a bond formed by the overlap of orbitals in an end-to-end fashion, as you can see in the diagram on the left side of the slide, with the electron density concentrated between the nuclei of the bonding atoms. A pi bond, which is different than a sigma bond, is a bond formed by the overlap of orbitals in a side-by-side fashion, as you can see in the diagram on the right side of the slide, with the electron density concentrated above and below the plane of the nuclei of the bonding atoms. Now, here comes the most important thing that you need to know to get the question correct about sigma and pi bonds. So take a look at those 3 bullet points at the bottom part of the slide. First point, a single bond, which is normally represented as a dash between atoms, that represents 1 sigma bond. Next point, a double bond, which is normally represented as 2 dashes between atoms, that represents 1 sigma bond and 1 pi bond. Third point, a triple bond, which is normally represented as 3 dashes between atoms, represents 1 sigma bond and 2 pi bonds. In the video description area, I will put a link to this video which may be helpful to you to help you visualize the concept of sigma and pi bonds. So in this video, the presenter talks about hybridization, and talks about sp3, sp2, sp, and then shows, using balloons as a model, examples of sigma and pi bonds. So in this picture, on the right side of the slide, you can see that the presenter is putting two carbon atoms together, and where those red balloons are touching, that is the end-to-end overlap that represents the sigma bond between those two carbon atoms. Then, as the video continues, they use these little skinny balloons to represent the side-to-side overlap, and that's what a pi bond is. So in this picture, on the left side of the slide, the yellow balloons represent the pi bond. So we have one sigma and one pi bond represented with the balloons in this video. And then the presenter goes on to show two different colors of those skinny balloons to represent one sigma bond, which are the red balloons in the middle, and then the yellow and the blue balloons represent the two pi bonds with that side-to-side overlap. So again, that video might be helpful to you to help you visualize what's going on in terms of the orbitals and the overlap. Now, on to question 12. Again, I'm reminding you of those 3 bullet points about a single bond represents one sigma bond, a double bond is one sigma and one pi, and a triple bond is one sigma and 2 pi bonds. Our first example in number 12 is this molecule, C2H6. I don't see any double bonds or triple bonds. So all we have in this molecule are sigma bonds only. And I see 1, 2, 3, 4, 5, 6, 7 sigma bonds, and there are no pi bonds at all. Now, moving on to the next molecule, which is C2H4. Now, I do see a double bond. Let's be careful how we count the sigma and the pi bonds in this molecule. So, starting with sigma bonds, which are single bonds, I see 1, 2, and then I'm going to count that double bond as 1 sigma so far. So there is a total of 1, 2, 3, 4, 5 sigma bonds, and then only 1 pi bond, which I am representing with a different color on the slide. Now, moving on to C2H2, that molecule has a triple bond, which again should contain 1 sigma and 2 pi bonds. Let's count the sigma bonds first. 1, 2, 3 sigma bonds, and then I see 1, 2 pi bonds. So this table now represents the correct number of sigma and pi bonds for each of these 3 molecules. Well, that is the end of this particular video. I hope that you found the answers and explanations helpful. Thanks for watching.